Welcome back. This is lecture 6, my course in statistical field theory or theoretical methods for soft condensed matter, depending on whether students are enrolled in the physics program or in the quantitative biology, the computational biology program. Today, we continue the analysis of the stochastic dynamics in the underdamped limit, which we started a couple of lectures ago by introducing the overdamped Langevin dynamics. In the previous lecture, we addressed basically two important questions that are intertwined in the way that we presented them. So basically, starting from the overdamped Langevin equation, which I write this way, we can define a probability distribution which is sampled by this stochastic dynamics given some initial distribution. And the questions that we addressed were two. Number one, what is comment this graphic, the partial differential equation obeyed by P of x of t. And the question 2, which I report down here for leaving room for my camera, is what is the quadrature form of the solution of such an equation. And by quadrature, of course, I mean path integral form, because the path integral is nothing but a very large dimensional integral. And both questions were answered simultaneously by first constructing the solution of a probability, by constructing the probability density P of t conditioned to start from some initial position at time 0, by employing elements of stochastic calculus and path integral formalism, and then realizing that the dynamics could be mapped into some formal quantum mechanical path integral in imaginary time. And this gives us the possibility of rewriting the probability in a form that was exactly a quantum mechanical path integral. And at that point, we knew the equation satisfied by quantum mechanical path integral because it's the Schrödinger equation in imaginary time. And then we could transform back and get the probability, the equation for the probability. We arrived to the following equation. This is called the Smoluchowski or Fokker Planck equation. I guess there's a beta here. Sometimes I forget factors of beta around. I guess this is down here. Doing things by heart is never a good idea. Anyway, let me see if this is readable down here. And let me get rid of this. Okay. So this is the Fokker Planck equation, the Smoluchowski Fokker Planck equation. And the path integral solutions for this, condition to start from some initial position, is the path integral for x naught to x in dq, the exponent of the negative of the integral from 0 to tau t in dt tau x dot plus d grad u over kt squared divided by 4. Okay, and let me remind you that this is basically what we did in the last lecture was to rewrite this in the following form. where the effective potential that enters here can be written in the following form. So, all in all, this is the equation that really illustrates the connection between quantum mechanics and imaginary time of a virtual system subject to a potential V. It's not really a physical potential, and diffusive dynamics of an overdamped particle. Now, by exploiting this connection, it is even possible to rewrite this in the following form. So basically what we discovered, that P of x of t starting from x naught is a collection of two exponentials. And I'm using the red color here because that's kind of a... And then I can use a quantum mechanical notation. Although this is not a quantum mechanical problem, I can still define a Hilbert space, why not, with operators and all that. The fact that this Hilbert space is not used to represent quantum particle but classical particle is completely irrelevant because mathematics is blind to physical interpretation. So I can always define bra and cat for classical systems. No particular problem with that. And this is the connection this is the equation that really makes clear the connection between imaginary time path integrals and diffusion. And this is my propagator. Which I know obeys imaginary time Schrödinger equation. And by exploiting this connection, we were able to derive the Fokker Planck equation. Now, there are many things we can actually discuss now. And the first thing I want to say is that the spectrum of the Fokker Planck equation, or better, the spectrum of the Fokker Planck operator, the set of eigenvalues of the Fokker Planck operator, is the same as the spectrum of the effective potential. How do I know? Well, because basically everything that we've said can be rephrased in the following way. Let me start from my Fokker Planck equation. And I can perform the substitution and equation 1 with substitution 2 will give me equation 3, which is a negative t psi h effective psi. Now, if you think a little bit about this fact, well, then you discover quite immediately that if you have a solution of the stationary equation then you can exploit equation 2 and get a solution of the stationary equation of the Fokker Planck operator. So basically the spectrum of the Fokker Planck operator, which is this guy here, is the same as the spectrum of the effective Hamiltonian in the dual quantum system. which has an important implication. Even though the Fokker Planck operator is not Hermitian, then since it's not Hermitian, we would imagine spectrum not to be real, because in general, there's no spectral theorem for non-Hermitian operators. But this is a very peculiar type of non-Hermitian operator because it doesn't violate neither unitarity, neither conservation of probability, to be more specific, to be more precise, nor the reality of the spectrum. Because this is a non-unitary PDE which can be transformed through a non-unitary rotation, in inverted commas, non-unitary transformation, into unitary form. So there is a dual unitary form of the Fokker Planck equation. And as a result of this, and as a result of this one-to-one mapping, the properties of this non-unity operator are basically the same. Many properties of the non-unitary operator are basically the same of that of a unitary operator. And to be more specific, the spectrum is real and the probability is conserved. However, since this is a non-unitary operator, there are things that do not transfer from Fokker Planck operator, from the effective Hamiltonian operator to the Fokker Planck operator. In particular, if you have a truly unitary operator, a Hermitian operator, such as the effective Hamiltonian, I'm waiting for the board to react, okay, then you know that you can basically construct left and right eigenvalues, or if you want, since this is self-adjoint, of course this is the same as this because these two operators are the same, which means basically the left and right eigenvalues are the same. So you can, if you have, well, let me not write the inner product Hilbert space version of this. Basically left and right eigenvalues of the effective Hamiltonian operators are the same functions. This is no longer true, though, for the Fokker Planck equation. And in particular, for the Fokker Planck equation, we have that the left and the right eigenvalues are obtained from the solution of the effective Hamiltonian through this unitary transformation. This is basically what we said when we said that P of x of t was e to the minus b half e of x psi of x of t. This is essentially the same statement. But then you can also show that the left eigenvalues, which are the solution of the adjoint of the Fokker Planck operators, which is not the same as the Fokker Planck operator because the Fokker Planck operator is not self-adjoint, but they can be constructed by the opposite rotation. And you can check this because if you do a joint of the Fokker Planck operator acting on Ln, you get same frequencies as before, as this. When I emphasize these are the same frequencies, and I should move this away for a moment. So there is some inherited symmetry, and deep one, that connects the eigenstates of this virtual quantum problem and those of the Fokker Planck operator. Both let them be left or right. And we will use this connection over and over because it will turn out that the left eigenstates, or the solution of the adjoint Fokker Planck equation, or also called the backward Kolmogorov problem, have also an important physical interpretation. The right eigenvalues, of course, are used to reconstruct the evolution of the probability density. We'll see that the left ones have interesting geometric and chemical physics applications, but let's not discuss that at this level. Let me just say, to be a little bit more specific and more down to earth, and address the following question: what is the physical interpretation of the eigenfrequencies of the Fokker Planck operation? Well, let's begin by the simplest case. Let's consider lambda naught. Well, first of all, we have a Hamiltonian bounded from below. So this Hamiltonian, we have a spectrum, we will have a ground state. And furthermore, the effective, we said that the spectrum of the Fokker Planck operator is the same as the spectrum of the effective Hamiltonian. So it's convenient to think about in terms of this, because this is omission and things are a little bit easier. This is an operator that contains a kinetic energy, which is positive definite, a spectrum, plus a positive definite potential. So this spectrum will be positive definite. So given that we have a positive definite spectrum, the question is, if we find a zero value eigenvalue, then we are sure that it's the ground state. And note, if you take this function, this is a normalization factor, the root of the Gibbs factor, well, this satisfies the following equation. So we have found the ground state analytically. How do I know? Plug it in and crank the handle. We have the definition of this. Remember the definition of the effective potential you can find back in the notes, either on the online notes for the course or in the previous lectures. Okay, once you have that, then you can plug it in, and you get you can easily check that the root of the Boltzmann factor is in fact a stationary solution of the imaginary time Schrödinger equation, and it's the ground state of the effective Hamiltonian. So it's also, from this observation, it is immediate to show that the right ground state is obtained with the prescriptions that we outlined before. Which, well, let me add the normalization factor. Remember, the normalization factors are constructed a posteriori. So let me write a slightly different normalization factor, which I will comment on. But the important point is since this is a root of this is proportional to the root of the Boltzmann factor, and this is a root of the Boltzmann factor, the result is the right eigenstate with the lowest frequency, lowest eigenvalue lambda naught for the Fokker Planck equation. It's the Gibbs distribution. And Z, of course, is the partition function in configuration space by normalization request. So we now see that unlike basically all quantum problems that are non-trivial, in this dual diffusion problem, we know the ground state analytically. That's a big advantage. And the fact that we know the ground states analytically is just a consequence of a specific structure of the Fokker Planck equation. Any other Hamiltonian you guess, you don't have that depends on a generic potential. In general, you're not able to build the ground state as a function of the generic potential you dial in. Sometimes you're able to find analytic functions that are corresponding to the ground state of that specific potential. Think about the harmonic oscillator. But that's only true for the harmonic oscillator. If you took a quartic potential, you cannot simply dial in a quartic potential at the exponent of the ground state of the harmonic oscillator and hope that you have a solution for the Schrödinger equation's ground state with that potential. On the contrary, for the Fokker Planck equation, this is the case. The ground state is always known. And this is a result of the specific and quite mysterious to me personally symmetry structure of the Fokker Planck equation. The fact that it's basically a continuity equation with a real spectrum, because it represents a very specific diffusion problem. With this in mind, we can now address the question that I was raising before, is what is the physical interpretation of the spectrum? Well, we have a physical interpretation of the lowest eigenvalue, which is 0. Now, if you plug in the dimensions, you discover that the effective potential, the effective Hamiltonian has units of frequency. So the eigenvalues of the effective Hamiltonian and the Fokker Planck Hamiltonian, they have a physical interpretation of frequencies. So what is the physical interpretation of a generic eigenvalue? Well, to see that, we do what we did for the imaginary time, I think, about presentation. I remember. So we go back to this expression. We write it as in the following form. This is again a very useful formula, because now I can insert the eigenstates of the effective Hamiltonian and get a spectral decomposition of the Fokker Planck propagator. I think we can get rid of the complex conjugate because there's a real Hamiltonian, and you can always find an overall phase rotation that sets all the eigenfunctions to be real, and that's of course what you want because the left-hand side is real. So, in principle, you can construct linear combination of the complex functions that give you a real function, but with different time dependency, this would be extremely difficult. So, you see. You can actually work directly in a real eigenbasis. But then, when you use this combination now, you combine this with this, and then you basically rewrite this as a sum over n. Then you have a right n of x, left n of x naught, e to the minus lambda n t. That's the spectral decomposition of the solution of the Fokker Planck equation, which will tell us that in the long time limit, this sum will converge to R naught of x, L naught of x naught, e to the minus lambda naught t plus correction. Now, this is the Boltzmann distribution. And by the same reason, if you multiply the root of the Boltzmann distribution, which is psi naught, and to get the left, you have to multiply by the inverse of it. So basically, you're canceling out the exponent, and you discover that L naught is actually a constant. So you can set it to 1. So let me get rid of this. And so what we're learning is that in the long time limit, this is actually the Boltzmann distribution, or the Gibbs distributions, plus corrections that die exponentially with time. So this expression tells us two very, very, very important properties of the Langevin dynamics and the associated Fokker Planck equation. The Langevin dynamics contains sufficient information to describe the relaxation to thermal equilibrium of a physical system. Because if you take any distribution, any initial condition, very far from equilibrium condition, and let the system propagate forward in time, if I wait long enough, the points that I will generate in my configuration space will be distributed according to the Boltzmann distribution. So I'm converging to equilibrium. And ultimately you can show, and we'll come back to that when we will be doing the quantum extension of open systems, that this is a consequence of having chosen the diffusion coefficient to be precisely dictated by the fluctuation dissipation relationship kT over m gamma. Or in other words, by having balanced the energy you pump into the system through the random kicks, through the stochastic noise, and the energy you take out from the system through viscosity. And if you balance them in this specific way, then the system will ultimately converge to equilibrium. This is a highly non-trivial property of Langevin dynamics, and this is one of the reasons that Langevin dynamics is so popular. It's a very simple way to couple a system to a bath in such a way that you're guaranteed to reach thermal equilibrium. In addition then, from these corrections here, we understand that the frequencies of the Fokker Planck operators, the higher eigenvalues of the Fokker Planck operators, are basically characteristic timescales which control how quickly your system reaches thermal equilibrium. Given different physical conditions, physical potential, you might have different relaxation times. For example, suppose you have a simple problem where you have a harmonic oscillator, then I expect relaxation time to be very quick. I put a system here, I get a bunch of points highly non in equilibrium, say my initial distribution rho 0 point is, I don't know, I only pick point with equal probability as long as their distance is between, I don't know, some distance from the origin, some L0 and L1, which would correspond to, say, picking points in a region here. Clearly, this is not the equilibrium distribution. But then I run the dynamics, starting from there, the point will quickly diffuse here, and if I wait long enough, there will be a Gaussian here, which is basically the equilibrium distribution. And the time it takes the system to converge to thermal equilibrium is dominated by the lowest eigenvalue of the Fokker Planck equation above the zero eigenvalue, so the lambda 1. This is called the relaxation time. Of thermal relaxation time. Other higher values of the spectrum are also associated with local relaxation. We'll come to that. Basically, if the system has a rugged energy landscape with many small and large barriers, then you have different relaxation times that corresponds to processes in which you locally thermalize. Sorry, this is not very clear. You locally thermalize within basins, and then you ultimately globally thermalize within the entire landscape. And in fact, for instance, if I have a different problem which I have a barrier between the two, then I expect the relaxation time to be slightly longer. to be very much longer. Actually, it is exponentially longer because the time it takes to cross this barrier on average is proportional to the exponent of the NH barrier. And in fact, in this case, you can show that lambda 1 and lambda 0 is much, much smaller than any other lambda plus 1 minus lambda n. So in other words, that the spectrum has a gap between 0 and the first eigenvalue, which means that the relaxation time type 1 is much, much larger than I write than 1, which of course means nothing. What I mean by that, it's a very long scale compared to all other typical scales in the system. So there are systems in which thermal equilibrium is reached within short time scales, and systems in which thermal relaxation is reached in an exponentially long time scales. These are systems subject to what is called to the phenomenon of thermal activation. And we'll come back to that in the next lecture, thermal activation, and explore the consequences of this and make some sort of a digression on the problem of thermal activations later on in the course. And I think for now I'll stop and we continue next lecture.